The modern world runs on a massive, interconnected nervous system. At sunset, vast continental grids light up, pumping terawatts into our homes, hospitals, and cities. But this sprawling network hides a massive inefficiency. Take a look at these transmission towers, the arteries of our power grid. As electricity travels through miles of these thick steel and aluminum cables, a huge percentage of that generated power simply dissipates into the air before it ever reaches a city. We have built our entire industrial civilization on top of an infrastructure that constantly bleeds its most valuable resource. Inside a standard copper conductor, flowing electrons constantly crash into copper atoms. These microscopic collisions create friction and heat, wasting billions of dollars globally. But in a superconductor, the internal structure smooths out. Electrons form perfect parallel lines, flowing effortlessly with zero heat lost. This frictionless state offers the first clear path toward a world where energy moves without resistance. Scientists have known about superconductors since 1911. The catch is visible right here. To force a material to conduct electricity without resistance, it usually has to be placed inside a dilution refrigerator, like this one, and chilled to hundreds of degrees below zero. Finding a material that works at room temperature requires testing chemical combinations across the periodic table. We're looking at millions of potential molecular structures. Mixing chemicals, cooling them down, and measuring their electrical resistance one by one in a physical laboratory takes months for a single batch. Human researchers simply cannot work fast enough to test them all, so they are handing the workload over to a tool built for scale. Artificial intelligence is now stepping in to map those countless combinations. The physical barrier of electrical resistance has become a computational equation. Instead of toxic chemicals, neural networks run detailed digital simulations, generating thousands of atomic structures at once. The algorithm evaluates how electrons behave inside each structure. It discards failures instantly, collapsing the grid down to a handful of predicted winners with clear, zero-resistance pathways. Recently, AI models used this exact process to identify thousands of brand-new superconducting candidates. They handed human scientists a highly targeted shortlist to synthesize in the real world. Algorithms processed a century's worth of trial-and-error chemistry in a matter of days. A practical room temperature superconductor offers a solution to the waste in our power grids, which currently drains billions of dollars in electricity every year. Inside computers, processing power is currently limited by the heat generated from electrical resistance. Without that heat, we could build stable, lightning-fast quantum computers. Heavy transport vehicles could operate on a fraction of their current power. Massive maglev trains would effortlessly levitate and glide above their tracks. We can already see the beginnings of this in medical imaging. This MRI machine relies on powerful superconducting magnets, but it requires expensive liquid helium to stay cold. A room temperature alternative would make this diagnostic technology cheaper and far more accessible. Zero electrical resistance is the physical foundation required to build the next generation of engineering. But a digital blueprint is only the first step. Once a material is discovered, we still have to figure out how to mass produce it cheaply, ensure it isn't toxic, and prove it can hold up in a real-world environment. AI can find the perfect molecular recipe, but human engineers still have to pour the concrete and string the wires. We are no longer limited by how fast we can mix chemicals in a lab. By merging algorithmic speed with physical engineering,
We are beginning to dismantle the oldest physical barriers to a zero-loss future.